So it's my pleasure to briefly introduce the panel. The panel is moderated by Steve Simon, who gave the introductory presentation. The other panelists are Gwendal Fève from the Paris experiment and Michael Manfra from the Purdue experiment. And they're accompanied by Moty Heiblum from Weizmann Institute, and Bert Halperin from Harvard University, Bernd Rosenow from Leipzig University, and Smitha Vishveshwara from University of Illinois. So they will provide a summary of their views of these experiments and the developments, answer any questions that have been left over, provide some critical analysis and outlook for the way forward. Steve?
So actually, we were just going to have Smitha give a couple, each of the four speakers, panelists would give a short presentation, and Smitha is going to go first, and then we'll take open questions. So go ahead.
Is it on full screen? Do you see the screen?
Yes.
Okay, great. Okay, so a deep thank you to the three organizers for such a thrilling and timely event and the invitation to take part. Following Steve Simon's beautiful introduction and context, we just had these two splendid presentations on observing anyons in the quantum Hall system by the experimental groups themselves. So now, as one of many, many who's participated and seen the wonder of how this whole field has developed, I'd like to give you a sweeping and very incomplete theorist's excursion, a brief recap, if you will, to share with you why these discoveries are so exciting. So to begin with, while bosons and fermions pervade nature, two dimensions allows the alternate quantum statistics of anyons explored since the 70s, and that can either pick up a fractional phase on exchange or have more complex non-commuting or non-abelian structure. So the fractional quantum Hall, as we all know, hails as an arena for realizing such quasi-particle excitations. And as shown over 3 decades back, including by my fellow panelist, Bert Halperin, in the simplest case of Laughlin states, of filling fraction nu, let's say, these quasi-particles come with fractional charge nu times E, and under exchange, they pick up the phase pi times nu. So now, how do you test this? Take fractional charge. You could measure fluctuations in a steady stream of a current of particles, and in a certain limit, they would exhibit noise that's proportional to the appropriate quantum. So short noise. And this works even for classical particles, like with, say, a mass of ping pong balls or hailstones or whatever you will. So in the 90s, Charlie Kane and my graduate advisor around then, Matthew Fisher, proposed this in the quantum Hall point contact geometry for the fractional charge of tunneling quasi-particles. And I was actually privy to their lovely Luttinger liquid edge state and non-equilibrium Keldysh formulation. The thing that's really amazing is that shortly thereafter, as you've seen by the Sekle group and my fellow panelist, Moty Heiblum and co-workers, this was actually measured, the fractional charge was actually measured in Laughlin states. Okay, so now that's for fractional charge. And what about fractional statistics? So while charge is really a single particle quantity, statistics really requires 2 particle measures. And there have been several marvelous proposals that have emerged through the decades and experiments as well. And we've seen this in the last 3 presentations. So anomalous Arnaud-Bohm period as set up by multiple groups, and as James reported to you in the previous talk. And then more complex geometries for Mach-Zehnder interferometers and telegraph noise, as amazingly realized, for instance, in Moty's group for electrons, for fermions. And then the one that I know best, and I'll say a little bit more about, partitioning noise. So to go back to the 1950s, and this is the famous Hanbury, Brown and Twiss, they were actually measuring correlation of stellar light in two radio detectors. And this was at the heart of what they first started off. And this was really at the heart of it, they were showing photon bunching. And these have really become the principles of quantum optics in beam splitter settings. So in 2003, I just started off as a postdoc in Urbana, surrounded by a lot of quantum Hall experts and Gordon Bain, an HBT master. And I thought maybe these astronomical concepts could be brought to the mesoscopic quantum Hall geometry by having two edges act as sources and two edges act as detectors. So I found out that a year before that, Ines Safi, Pierre Deviat, and Thierry Martin, they'd actually pioneered this in a really beautiful treatment of a single edge state source partitioned into two others. And then Eduardo Fradkin, Una Kim, Mike Lawler, and I looked at this a little bit for a similar setup and in more detail. And one of the things that comes about, which Una Kim really did admirably, among other things, was that there are these anionic Klein factors that come into play, and it's really important to get these sort of time-ordered events right. So cross correlations do show anionic statistics that's intermediate between bosons and fermions, but I should say that gleaning their effect is not always easy, because in a sense, the Luttinger edge state physics entangles into your correlations. And in a sense, it acts as sort of source and detector response functions. I should mention that if you look at the actual quantum Hall bulk, that's much, and you're looking at anionic coherent states, for example, that's much cleaner. And in a sense, the quantum point contact there acts as a saddle potential, which is effectively a beam splitter. So there's been a tremendous amount of theory and experimental development on this. And the one that I do draw attention to is this work by Bernd Rosenow, and who's also on the panel, and he'll tell you more, and Ivan Levkivsky and Bert Halperin. And the reason that I really love this work is that, first off, it's a really clever setup for focusing on, and we already heard this in some of the previous talks, to focus on the one single quantum point contact, but really you have dilute beams coming in from others. So it's a really clever setup. And the other thing is that it really hits on the right correlators. So the thing that I told you about the edge state coming into play, all that sort of washes away, and you're purely left with some quantity which under certain limits can measure that statistical angle in and of itself. Equally important, these are, as you heard Gwendal talk about, these are really the guiding principles in the beam splitter-like experiment of Fève's group. And I should say that when these experiments first came about, I really jumped for joy. It was so wonderful to see this sort of affirmation. And then, as if that in itself wasn't enough, shortly thereafter, we had Michael Manfra's group, and you heard James talk about this, also showing this very alternate sort of evidence. And so it's really, for me, for the field, I would say, it's so beautiful to see that there's been a leap in corroborating that these fascinating quantum creatures might actually exist. So do exist. So then what next? There's lots more understanding these experiments further, and what next? Steve Simon mentioned this whole quantum Hall being a technology in and of itself, and then can these anyons be realized in other sort of arenas, like perhaps photonics or the like? So I think the panel will be very lively in having these sort of discussions. What I like to leave you with is that for decades, many of us have asked with regards to these fractional quantum Hall quasi-particles, anion there. And I think we've come a long way in the field. And so far, and I would say that now there's really strong evidence to sort of say that, yes, we do believe so. So thank you.
Thank you, Smitha. Next up is Bert. No slides from Bert.
See, that's correct. I have no slides, and I do just need to get one thing straight here. Yeah, just a second. Whoops, sorry, I'm having a little trouble with my computer here. Just give me a second, and we will get it right, I think. Yes, okay, thank you. So again, it's really, I thank the organizers of this conference. It's been a very exciting conference for me to see. First of all, there was 3 beautiful talks by Steve and the 2 experimental groups, and a very nice summary of it also by Smitha. I think these are exciting developments, and it was beautiful presentations. I have really not that much to add to what's been said. I'd like to, well, one thing I'd like to just sort of remind people of, we all knew, I think you mostly all know, is the issue of whether quasi-particles with fractional statistics exist in fractional quantum Hall states should not be seriously in doubt. And what's really interesting is to what extent, in my view, what's really interesting is to what extent you can see these effects directly in experiments. And I say this because there is essentially rigorous arguments that if a fractional quantum Hall state exists, which has associated with an energy gap, at least in the absence of disorder, at some filling fraction, let's say P over Q, where these are integers in their lowest, without any common denominator, then there must exist charged excitations with charge E over Q, where Q is the denominator. And these must obey fractional statistics with a statistical angle of the form pi over m, pi over q. It would be pi over this denominator. The argument for fractional charge was, of course, first given by Laughlin with his Gedanken experiment, in which you insert a solenoid of infinitesimal size in your quantum Hall state, and you add one flux quantum adiabatically. And if it's the frequencies are well below the energy gap, you don't. You stay in a new ground state, but it's a ground state with extra charge, and you can then remove the flux quantum by a gauge transformation. So this is really a rigorous argument that you will accumulate 1/3 of a fractional charge, for example, in the 1/3 state. And you can extend this argument. It's a bit more complicated, but similar in spirit, to argue that it must have fractional statistics. So if you believe logic, and basically, essentially what I would say rigorous mathematics, I would say that any experiment which convincingly establishes the existence of a quantized Hall state at some particular filling fraction is logically a convincing demonstration of the existence of quasi-particles with fractional statistics there. So having said that, of course, then the question of what we would like to ask is, what do we consider a direct observation of anyons? We would certainly say that just seeing a quantized Hall state is not direct. And this is, of course, somewhat, I would say, of an aesthetic question of what you consider direct. And one can have different views on this. I would argue that this Purdue interference experiment, seeing jumps in the interference exactly very near what you predict from this Anyon phase is just about as direct as I could possibly imagine. Now, of course, it was a very non-trivial to create the proper geometry, you need a sample of very high quality, device small enough for interference effects to exist, but still you have to remove the Coulomb interactions and make sure they're adequately screened. And that was very difficult. And then, but having achieved that, I would say the interference jumps they see they admit a very simple interpretation. You don't need anything very complicated to explain it. And that is certainly direct. Now, it's not rigorous because you could say, well, there are also Coulomb interactions that are residual, and you cannot completely interact. There would be the possibility that the interference jump has to do with the Coulomb interaction. So it's remarkable that it would be the right size. But so you could always say there might be some possible alternate explanations. I think it doesn't. I think it looks pretty good, and also the fact that things look good when they get out of the central regime and they're starting to lose. Well, they see the change in slope. All fits together with a simple interpretation, and I would say that that's really direct. Now, when you get the Anyons collider experiment, it's obviously more complicated. It's a beautiful experiment. I would say it's less direct because the predictions really involved rather complicated calculations that didn't just take into account the fractional statistics. You had to certainly take into account the fact that the charged quasi-particles move along edges, which are these Luttinger liquid type edges. So there are phonon-like modes, which, and when a quasi-particle tunnels from one edge to another, it leaves behind a trace in these excitations, which must be taken into account if you want to understand the tunneling rates. And so certainly the fact that you get, so in the calculation that was used to interpret the experiments were restricted to a Laughlin state of the form 1 over an odd integer, and the cross correlation, it was predicted to depend on that integer, but the integer determines, of course, not only the fractional charge, but introduce the fractional statistics, fractional charge, but also affects what the edge state is like. And it's not clear whether, at least I don't know, maybe other people do know, whether you'd get the same result for edge states with a state that's not of the Laughlin form. Would be the same relation between the final factor and the fractional statistics. Calculations suggest that I think it would be modified if there was some edge reconstruction. So, but again, I want to say that doesn't, the fact that maybe this is not such a direct measurement of Anyons statistics doesn't make the experimental results any less interesting or important. On the contrary, I think the fact that they agree with a theory based on more detailed experiments gives important credence to these experiments, and to me is even more important and more exciting. And let's see, I guess the only other remark I would make, just to emphasize something that was maybe was sort of said before, is the interferometer experiments measure the statistical angle, what I call the statistical angle, modulo pi, whereas the theory actually predicts it modulo 2 pi. In other words, what they're measuring here is the angle of bringing one anyon entirely around another. And that would not even distinguish fermions from bosons, whereas the actual statistical angle is defined modulo pi when you interchange two particles. And so that we don't have a direct measure of, but we certainly do have a measure that it's different, that we're not dealing with fermions or bosons. Thank you.
Okay, thank you, Bert. Next speaker is Bernd Rosenow, and I think you do have slides.
Yes. Okay. So first I would like to thank the organizers for putting together this exciting conference, and I believe the other speakers and also my fellow panelists very much succeeded in conveying the excitement, which certainly I felt when I heard about these beautiful experiments first. And I would like to use my time to say a few words related to sort of the theoretical foundation and what is seen in the experiments. And I would like to start with the collider experiment from Gwendal Fève's group. So we all know from experience or from learning about fermions that there is a relation between the exchange statistics, the minus sign which the wave function picks up for fermions, and spatial exclusion as formulated in the Pauli principle, such that I believe it is a very valid idea to measure anyonic statistics or to try to relate anyonic statistics to the degree of spatial exclusion of particles. And I would like to say a few words about how this statistics enters in such a collider experiment. So really well defined is the statistics in the two-dimensional bulk, in the gap bulk, where anyonic excitations are well defined and where one can think about spatial interchange of two anyons and where the wave function picks up the phase factor, which would be pi/3 for a Laughlin state. And due to bulk boundary correspondence, this bulk statistical behavior is reflected in the correlation function of anyons on the edge, which for the Laughlin state is a third root of the difference between spatial position and time. And if one now looks at the equal time correlation function, sets time equal to 0 and considers an interchange where the spatial coordinate goes to its own negative, then there is a minus sign underneath this third root, and taking the third root of -1 is indeed the anyonic exchange factor, which is well defined in the bulk. Obviously, on a one-dimensional edge, it is not possible to actually interchange anyons, but this bulk behavior due to bulk boundary correspondence is reflected in this edge correlation function. Now, when thinking about a collider experiment and looking at the details of the calculation, one finds that indeed the current course correlations, which were measured experimentally, are related to this edge correlation function. However, in this case, it's not the equal time correlation function, but the equal space correlation function. But due to the chirality of the system, both of them necessarily have the same power law behavior, which in turn is related to the bulk statistical angle. Now, an interesting complication can arise in the presence of edge reconstruction, which means loosely speaking that there is a compressible region outside the current carrying 1/3 edge mode. And this topic has been much studied recently under the context of neutral modes. And I'm sure Moty, who headed many of these discoveries, can say much more about this. But from a theoretical point of view, if there is a dynamical compressible region in the vicinity of these edge states, the dynamics of the edge correlation function can be changed. And this universal exponent, which reflected bulk statistics, can be modified. And it turns out that it is always modified in the way of being increased. And when we did our calculation, we indeed allowed for such a general exponent and also allowed for the possibility that these extra states might screen the quasi-particle charge such that it might deviate from the exact value. And the universal prediction arises if one assumes that there is no edge reconstruction. And from this point of view, I think it is really important that the experimentalists made the effort demonstrating that there is probably no edge reconstruction in the experiment by looking for upstream transport of heat. And I think that's really an important contribution to emphasize that what they measure has a good chance of being related to this statistical bulk angle. So I'm really impressed by this experiment. Then maybe a few words about the interference experiment. So I think Jim Nakamura did really an excellent job. He essentially said everything I was planning to say, so I can rely on what he told us. So if we look at the interference phase, which enters the expression for the backscattering probability and for the voltage drop, then there is the Aharonov-Bohm term multiplied by the fractional charge. Then there is the anionic term, so it's 2 times the statistical phase for interchange because it's a full loop. And then there is a possible Coulomb correction, which I don't want to discuss in much detail now. So as Steve beautifully explained, there are 2 general regimes, the so-called Coulomb dominated, which maybe is not so suitable, or at least it's not so easy to extract information about exchange statistics, and the Aharonov-Bohm regime, where this coupling parameter, which couples charges in the bulk to charges on the edge, is small. And now, interestingly, this Aharonov-Bohm regime again comes in 2 variants. One variant is where the density is constant, which is due to some residual Coulomb interaction, and there is a second variant where the chemical potential is constant. So that's in the limit where a Coulomb interaction is really weak. And in this beautifully designed experiment from the Purdue group, there are these extra screening wells which allow to reduce the Coulomb interaction and allow the observation of an interesting competition between charging energy EC and the quasi-particle gap delta. So I would like to say a few words about what happens in this regime of constant density. So the idea is, if the magnetic field is changed such that there's an extra flux quantum, there will be, due to the quantized Hall conductivity, charge flowing into the inside of the interferometer cell. And in the regime of constant density, this extra charge needs to be compensated by creating a quasi-hole. And then there are 2 contributions to the interference phase. There is the anionic one, there's the Aharonov-Bohm one, and there's the contribution due to the quasi-hole. And they conspire in such a way that the magnetic field period is expected to be phi naught, which in principle is evidence for anionic statistics, because one would really expect 3 phi naught. But on the other hand, you could argue it looks like electrons, it's a system of electrons. So observing a period of 1 flux quantum is not that much of a surprise. So relating more closely to the experiment, there's this competition between charging energy and gap. And if one does the calculation of the electrostatics, one finds that there actually can be a phase transition between the regime of constant chemical potential close to the center of the plateau and the regime of constant density when moving away. And there should be a change in periodicity from the pure Aharonov-Bohm period of 3 flux quanta to a reduced period of 1 flux quantum, as explained. And obviously this figure here is a theorist's dream operating at ultra low temperature and not in a regime of thermal suppression, as Jim explained, is found in the experiment. But anyhow, in the vicinity of this transition, one would expect disorder effects, localized states, to allow some quasi-particles to enter on an irregular basis before fully entering the new regime. And this irregular entrance of anyons would give rise to the observed phase slips. And what I really find so beautiful about this figure, you really only need a ruler to measure the distance of the phase slip and take the ratio to the distance between these 2 lines. And that gives you the anionic statistics modulo of 2 pi. And so I fully agree with Bert that that's a beautifully direct measurement of this anionic statistics. And yeah, with this, I would like to conclude my views on these experiments.
Okay, thank you. The last panelist is Moty. Moty, do you have slides you want to show, or is...
Okay. No, I don't have any slides. So I'll take a little bit, everything was said about the experiments by now. So I'll take a little bit of a bird's view, if you don't mind. First of all, when I look at meetings in general, when I see a gallium arsenide talk, I say, wow, there is a gallium arsenide talk now. Okay, so this is very nice that severe important discoveries still appear in gallium arsenide, two-dimensional gallium arsenide. So I don't feel totally alone in this area. There is also other people that are interested in gallium arsenide. And gallium arsenide still is probably one of the best media to work in because of the super high mobility, the cleanliness of the system, etc. Now, we can be more specific about the experiment itself by saying how great they are and also raise some critiques. But now, just in general, I would say that being in this area for many, many years by now, and justifying every time why I don't see statistics, being it most of the time neutral modes, which may be avoided. They might not necessarily be in every particular edge mode. In 1/3, you're not supposed to have neutral mode. They're not topological there, but they seem to appear in any of our structures. The point is that these experiments that we see are correct in some regimes, okay? These are what I find lacking in all these experiments, mine too. There is nothing, you know, to bicker about, and because I don't know how to improve it even at the moment, but there are some regimes that you see this work, some regime that collision work, and some regime that interference work. For example, I fail to understand why Coulomb is not very dominant. Coulomb interaction is not extremely dominant when you have Coulomb, when you have interaction, you have collision. Because you come to a simple QPC, and the only events that are important are one hits the other. When you have 1, 0, 0, 1, you don't care about it. They hit one another. They sit in a very small range, and we don't see Coulomb effect. Okay, so maybe I should see this P minus something, but to see P minus 2 exactly to the dot is very surprising. I don't think that I am convinced by seeing it, and that how can it happen? It's very interesting. A similar thing that when you see interference experiment, which I wrote Michael Manfra after his first paper, I would like to see if the quasi-particle charge that partitions in the QPC is really E over 3. And you can say, well, this is a filling factor E over 3, but it doesn't mean. Many times I measure charge when there is E over 3, and I look at the transmission is not super constant with energy, and you see something else. And even Gwendal showed that you can see even electrons, right? If it is not totally linear, you see electrons, and he explained the deviation from this P equal minus 2 by electronic behavior. So I think that there are things to improve, but what had been done until now is beautiful. It's nice. It's about time that it should appear, and we should think about something, continue more and doing it more robust. That's all. Okay,
Thank you. Maybe we have a long list of questions here to run through, and we're running a bit out of time. So maybe I'll just take some of the ones that are obviously good ones. So one question is to Mike and James. Actually, there's two questions which I'll merge together. One is whether the experiments that you've done with these screening gates, whether the presence of the screening gate mucks up the mobility enough that you won't be able to see some of the more subtle fractions, like 5/2 in the lowest in the higher lambda levels. And a second, that's a question from Gunnar Muller, and from Carol Stingel. There was a question of whether you it's a similar question. The data for the gated device. How good is the mobility under the gated device?
So negated device. So in the ones we used in the experiments, the mobility of the primary quantum well is about 8 million. So that's certainly good enough. And that's at around 1 × 10⁻11 or slightly below 1 × 10⁻11. So it's a fairly good quantum well for that density, given the construction and all the processing that's gone on, fabrication that's gone on to it. So that's certainly good enough to see the primary fractions. We can see 1/3, 2/3, all 2/5, all those states. Whether we can actually create one of these structures that's of sufficient quality to look at fractions in the second Landau over the first n=1 Landau level remains a challenge. Whether we're going to be able to see 5/2 in such a structure is not clear yet. We haven't yet. It's hard. We have to actually get the density higher in the primary well, and it's hard getting enough charge in there using the screening well technique. So that remains a challenge, that we're trying to devise a structure in which you could incorporate these screening wells if we wanted to, in fact, use these screening wells and have a sample that is good enough for second Landau level physics. So that's an outstanding question at the moment. For the primary, all the composite fermion series, that the ones even the ones we want to look at next, 2/3, for example, 2/5, I think we have sufficient quality.
Actually, as long as you're still talking, do you have any comments responding to Moty's question of how well do we know that it's and there was another person who asked the same question. I can't find it right now. Junzu, actually, I think that especially given that Gwendal's data seem to show that even with the same point contact, you can sometimes get, it looks like electrons going through sometimes, and it looks like 1/3 charge going through other times. Do you have some way to calibrate that what you're looking at in each point contact is really transmission of E/3?
Yeah, I would say we haven't looked at it extensively. We're usually looking at fairly weak backscattering limit. As we have gone to larger backscattering, we haven't seen much change. We'd say you agree with that? Yeah. So as we increase the backscattering, we haven't actually seen a dramatic change. So I don't think we have evidence for this transition, at least in the data we have so far.
Okay. Actually, a question to the theorists, which I liked, so I'll read it out, from Chris Lauman, is to what extent is the noise experiment measuring exchange statistics versus exclusion statistics, or is there any way to even distinguish between the two?
Should I say a word on that?
Oh yeah, go ahead.
Yeah, so Chris, I think that's a really good point. And so just to clarify what that even means, I think, Chris, what you mean is for the exchange, you're actually taking one particle around the other, and then you're picking up this phase, compared to, say, exclusion statistics, where you may have some n number of anyons, and then you're trying to add an extra one, I think. And I think this is the distinction. So I think it's a great point, and actually, explicitly, I see that in many of these edge state calculations where one is looking at, I would say, exchange, I think, and the other theorists or anybody can jump in. And in a lot of these calculations, you kind of, when you're looking at cross correlations between multiple edges, you're actually putting in these Klein factors that have that exchange. I should remark, I mentioned a little bit about bulk sort of anion correlations, and I'm still trying to, in my head, connect those results with these edge states. There you actually do see instances of exclusion statistics pretty clearly. I do also see that Yuval can add to that. So maybe Yuval or Bernd, anybody else. But I think that's a great question, and one does have to be very clear about disentangling the two. And I think what we are looking at is exchange.
Well, I would say I'm not quite sure that I could understand the difference in this context. I would understand it perhaps it would, if we're looking at collections of particles in the bulk, and if there are many of them, but once you're getting involved with edges, I'm not quite sure what you mean by exchange. In this case, exactly what you mean by it. So these are all linked together. The theoretical explanation involves a particular model in which these are linked together, also linked to the exponents on the edges. So I don't know, I think it's all mixed.
Another question here, which may go to either Gwendal or to Bert or Bernd or Smitha. The question is, if one does the collider experiment with, and I think this is from Yuval Ronen, if one does a collider experiment with, at say 5/2, ideally, would you be able to get interesting information out of that?
So I leave the word for the theoreticians because I'm very interested in their answers. So we would like, of course, to see signatures of 5/2, possible signature of 5/2 in these collision experiments, but I do not know what to expect.
Well, I would say that Willett has done that. That's what Willett has done or claimed. He has done precisely that. He is doing, it's not a collision experiment, but he's doing the interference experiment, and there he is seeing something. Maybe I misunderstood the question.
So no, it was specifically asking about the collider experiment.
Okay, I'm sorry, then I back off.
So maybe I can tie a partial answer. So, I mean, I haven't done the calculation yet, so I can't give you a final answer, but the hope would be, I would believe that the result would be different from 1/3, at least. Obviously, it's just a number, this P. So you cannot expect something qualitatively different for the 5/2 state. And I think it will be important to figure out, for instance, whether these numbers are different for different candidate states for 5/2. And I think that needs to be seen by going through each and every plausible candidate state and checking whether they would be distinguishable.
There was an experimental question, I think, to Mike and James, I think also from Junzu, saying that how does the gate work through the screening quantum well? How do you make that work?
So how does the gate work?
Yeah, she says, how does the gate work through the screening quantum well? Does it act as a floating gate or? No,
well, the screening well is grounded. It's connected through the drain contact. So it is, the gate punches through the screening well, creates a hole in it, and then.
So you have to deplete the whole screening well to gate.
Well, where the ohmic is, around the ohmic, yeah. And that depletes the screening well right there at the ohmic, as Jimmy showed in one of the early view graphs. But the screening well itself, or both of them, are connected to ground through the drain contact.
Okay, then I'm sort of running out of, oh, there's a question from Eduardo, also to the experimentalists. He says, Eduardo Fradkin, he says, I have an annoying question. And I'll translate it also, I think. The question is the density of the screening well large enough so that the quantum Hall effect is not observable in the two-dimensional electron gas? I believe what he's saying is that if you can destroy the Coulomb interaction enough, since fractional quantum Hall effect depends on Coulomb interaction, you should be able to destroy you should be able to reduce the gap of the fractional quantum Hall effect down to nothing. Is that possible? Or do you even see a change in the gap as you?
The gap that we measure, we actually extract the gap of the two dag, and it's consistent with what you would see in single layers for a given density. So the short range part, the screening seems to act on the long range part of the Coulomb interaction. The short range seems relatively intact. We see basically the same size gap as we would in a single layer when we measure activation energies.
Yeah, Actually, to Eduardo, I mean, I think the gap depends mainly on the very short range part of the Coulomb interaction.
So that's, I mean, and that's consistent with what we see. Looks just like a single layer in that regard.
A question to both of you from Yong Chen. What do you get at 2/3? To both groups.
So we're working on 2/3 right now, and it's much more complicated. The edge structure is much more complicated. We do have signs of interference, but it's not as easy to interpret. That's an ongoing experiment right now. So it's complicated, and we're trying to just understand what we have at the moment and then create an experiment. And so we did in our first experiment, we looked at 2/3, and what we saw when we went to a little bit stronger backscattering, we did see AB interference, but we saw it consistent with a charge E. So, you know, if we consider the system built as U equals 1 state plus a 1/3 whole state on top of it, perhaps we're only interfering the U equals 1 edge, and we're only sensitive to it. So we still have a lot to figure out about what's going on at 2/3.
Gwendal,
regarding the collision experiment, then so this was discussed by Bernd as well. So the theory can take into account basically any situation, abelian situation, depending on this screen quasi-particle charge lambda and statistical parameter delta. So this should be different in 2/3, and in particular, the lambda parameter could also be different, because one reason to go for 1/3 is that the edge structure was simple. So in principle, we did not care about a reconstruction mechanism that could change this lambda parameter, for example. The situation should be different in 2/3, where you have several modes, neutral modes and counter-propagating modes. So that's interesting to test the theory in a regime where this parameter could be different.
Actually, Gwendal, one question.
Make a comment on this, Steve. I'll add a comment.
Go ahead.
That in 2/3, the neutral mode is topological. Okay, so it's there. It must be there. We cannot get rid of it. We try to. We can get rid of the 1/3 if you sharpen the potential, but we cannot rid of the 2/3. It might not bother you on interference because the wave, you know, the wave packet might be longer than the interferometer, etc. But in the collision experiment, I'm sure it's going to have an effect, because the neutral mode will come through a QPC and it creates charge noise immediately and blur the whole thing.
Mm-hmm. Thank you. There's actually another question to Gwendal. It's an easy question from Chang-Ki Hong. Could you comment on the 2-deg depth from the surface?
Yeah, it's approximately 100 nanometers below the surface.
Okay, thank you. There's a question from Adi Stern to Mike and James. The question is, can you continuously pinch off the quantum point contacts to approach the Coulomb blockade limit? And what happens to the oscillations and phase jumps as you do this? You're muted.
We haven't studied it with really strong backscattering. In principle, we could, but we haven't done that yet to go to a very strong backscattering limit. So I guess we don't really know the answer. We don't have a good answer to give them right now. We've mostly been working in relatively weak backscattering. So in principle, it can be done, and then we should do it and can report later on what we see.
Okay. Actually, maybe I should ask the people on the panel if they have direct questions for each other, because or direct answers that they want to give to each other after things have been raised. No. Then another question for the organizers: how much are we allowed to go over our 5:30 ending point?
We still have a lot of people in the audience, so I guess it's up to up to everyone involved if they'd like to stay a little longer and continue answering questions as we have them. Okay. If everyone, it's up if the panel's willing to stay on a bit longer.
I'm also running out of questions that I
Sure.
I mean, there are still more questions, but some of them have been either answered or addressed, or I don't quite understand what the questions are. In some cases,
I can add something, because I saw a question by Yigal Meir. I don't know if Yigal Meir is still around, but he asked, not necessarily me, why do we never see interference in 1/3 in the Mach-Zehnder? Is Yigal still there? Okay, anyhow, this is true. There is always a Rosenow in Mach-Zehnder, because you have this OMI contact that drains out all the carriers if they have to. However, we see always interference that is anywhere from higher Finney factor all the way to Finney factor 1, and at 1 it disappears. And then we see that above 1 Finney factor, neutral mode appears due to edge reconstruction. Okay, so this is not, again, a necessary thing. It's not topological. So maybe by doing tricks like Manfra's group was doing, or else, that we can somehow suppress the neutral mode that appears in the Mach-Zehnder, maybe it will help us. So far, we didn't do it.
There's a question. Go ahead.
You can see that there's a difference, I think, in sort of the pinch-off character or the conductance characteristics of the QPCs. I think your melting of interference paper, I think, is a good example of that, where you see this long decay in the conductance below nucleus 1, and even the appearance of a 1/3 plateau. It's, at least in our screening well samples, we seem to see very sharp turn on or turn off of the conductance at nu equals 1 and 1/3. So the conductance plots look quite different in the two cases. And it seems like this screening well actually dramatically alters the confinement potential, which can have a dramatic impact on whether you see a reconstruction or not.
There's a question actually raised by Charlie Marcus. It was aimed at Bernd Rosenow. It says, can you elaborate on, quote, it is not possible, or at least not easy, to extract statistics information with a non-zero Coulomb term. Part of that was in quotes. Is it difficult or impossible, parentheses, all experiments are difficult? So I'd like to give Bernd a chance to answer that back to Charlie.
Hi, Charlie. So in my understanding, if you take interference periodicities or gate voltage periodicities as the signatures you're looking for, then there's always a leading periodicity, which would define whether you are, say, Coulomb dominated or Aronoff-Bohm, but there are also sub-leading periodicities. So what one would need to do, Fourier transform, and look for satellite peaks, which are there in addition to the strongest peak, and they might contain information about behavior which would be dominant in the Aronoff-Bohm regime, but which is still present as a subdominant behavior in the Coulomb-dominated regime, say. And in that sense, it's even harder than the regular experiments, because you need to look for subdominant or subleading behavior in your signal.
So thank you. There's a question from Janandra Jain asking if we know if there's edge reconstruction in experiments. I know from Bernd Rosenow's comments that in supplement 8 or 7, I think it's 7 of Gwendal Fève's, or maybe it's 8, science paper, they carefully look for edge reconstruction and find that there is none, at least by not seeing upstream neutral modes. But Mike, I'm gonna send this question to you. Do you know anything about whether there's edge reconstruction in your experiment, or do you have suspicions as to whether there is or not?
I'm not sure we have a way to probe it right now. I'm not sure we can say whether there's definitively say that there isn't an edge reconstruction, only by looking at our conductance plots at 1/3 and seeing the sharp fall off. But we haven't way of probing neutral modes.
Is that you might suspect, given that you feel that the edge is sharper, that there are none?
That's our belief, yes, but there's no definitive proof of that.
Right.
I may have a suggestion for Gwendal about the neutral mode, because I looked at your supplementary 8, and you have a quite involved measurement to look for neutral mode, which was difficult for me to follow. But if you just go to 2/3 and you know that there is a neutral mode there, and you can see if you measure right away neutral mode, then you go to 1/3 and you see if it's gone. So it's very simple rather than playing around with 1/3, closing QPC, opening QPC, all this stuff. So it's a very simple experiment.
Yeah, okay, so this is something we can do. Just for the method, we had basically two methods. I think one is the one we use. We just generate heat on a contact and see if we can see it in noise measurement going counter-propagating. So I think this is the type of technique that you are using as well, no?
No, we just go to 2/3 and we see neutral mode upstream. That's all.
Okay, so we can do that.
There's another question from Val Fatimi. Again, the interferometry experiment, do the phase slips become less sharp as a function as you increase the temperature?
Yes, everything gets washed out as we increase the temperature.
But maybe in what way do they get washed out? Does it look like they get smaller as just everything smears out, but they're everything's still in the same place, or does it look like the amount of the slip is changing as well?
Sorry, pressing the wrong button. Just seems to get smeared out. That's all we can say right now.
Okay, let's see. I think we're running out of good questions here. Maybe since it's oops, there's a question just about to a question from Anton Akhmarov. Is there anything we could learn that would help probing properties of the bulk excitations? i.e., is there any way to control individual ones? So is there any way to control individual bulk excitations?
Great.
Yeah, I guess the one thing would be the antidote.
We can try building antidotes. You need to localize individual quasi-particles would be antidotes inside the interferometer. It's one thing that we're trying to do so that we have, rather than allowing them to come in randomly or associated with disorder, actually control the number.
Okay, good.
So that's something that devices we're building now.
All right.
I can add also, there is a comment, if you go, sometimes Coulomb interaction is not bad at all. Because if you go to pure Aronoff bomb with infinite capacitance, if you wish, you can just change the magnetic field and add carriers up to whatever you want. Nothing will happen. You just pile off carriers inside and inside, everything is compensated by this fantastic capacitor, okay? So you need a little bit of Coulomb interaction. So you charge the dot enough until you release this charge by having a quasi-particle excitation, okay? So you have to charge it enough to above the gap to get a charge, a quasi-particle. So you, Manfra, you, Michael, had something like, if I remember in the first paper, at least you mentioned 17 microvolt and it was in these two. So you need to add few quasi-particles inside, okay, to add maybe 10 or something like this. And then you are going to excite quasi-particles out. You're going to charge the dot enough. So you will need a bit of it's a fine tuning between A, B, and CD. But you cannot be pure AB and you cannot be pure CD.
Mm-hmm.
Okay, maybe I'll end on a softball question or a Rorschach test question that everyone can speak to. Question from David Chester. Is there any hope that similar experiments could lead to the detection of non-abelian anyons?
Well, as I've already said, in terms of the interference experiment, there are these experiments that Willett has done, which if they're being interpreted properly, show just that. Of course, there are issues. The main issues there, I think, are that we don't really understand why his dots are so small. I think there are questions about what is really going on, and to the extent that somehow the size of the dot is much smaller than you would expect theoretically, or that you could control. So there are issues there, but they are certainly experiments which show the effects predicted for non-abelian particles. And now you have to say whether we understand them properly. And if more experiments that clarify that would certainly help. But as you said, it's more complicated with the collider experiment because it hasn't been worked out yet.
Okay, maybe that's a good place to close the session.
So, Steve, I just wanted to, maybe if we're ending, just make a few remarks. So just thanks to all the speakers and the panelists for giving such excellent talks and a great discussion. And thanks to the Virtual Science Forum for hosting this great event. So it's really great to see all this really exciting progress in fractional quantum Hall, which is a very difficult field, and the problems have been around for many years. So hopefully we'll have even more great experiments coming out in the next couple of years. So maybe we'll have observing Anyons 2021 if you know, we have more progress like at this level. Yeah, so thank you very much.
Thank you.
Thank you.
Thank you.
Thank you, everyone.
Thanks.
Thank you.
Everybody. It was great.
Thank you.
Thanks.